At NASA, machine learning is becoming a new tool for atmospheric scientists to understand processes of oncoming severe weather. In FDL 2020, our researchers showed how the jump signature of lightning flashes detected from space can be excellent predictors of oncoming severe weather events, such as tornadoes and hail. NOAA's Geostationary Operational Environmental Satellite, or GOES, has a camera called the Geostationary Lightning Mapper, which captures and records the intensity of light above a certain threshold, which is classified as lightning. But some lightning is lost. So we asked the question, can we achieve a greater classification accuracy of true lightning events by applying machine learning? I'm pleased to introduce the result, the Geostationary Lightning Mapper Instrument Upgrade.
And Lightning team, you're good to go.
Hello, everyone. We're the Lightning team. My name is Emmanuel, and thank you all for joining us. We're electrified to have you here. Without further ado, let's get right into it. So extreme events have affected mankind since the dawn of time. For example, tornadoes are one of the most deadly and hard to predict storms in the USA. Wildfires are frequently occurring events which destroy acres of our precious forests and wildlife therein. One key component that each of these phenomena share is that increased lightning activity can be used to predict the onset of these extreme events. So our goal is to improve our ability to detect lightning early in the development of a severe weather event and to provide timely warnings to save the lives of affected residents. We now have the technology to pick up on these lightning events even from space. The Geostationary Lightning Mapper camera, in particular, is specifically designed to measure photons reflected from the Earth. And thanks to these innovations, we now have more coverage of events, more frequency of events, and a lot of data. So this is what the sensor actually sees, including the strobing. Yeah, that's real. Shocking, I know. What we see here is a time lapse over the course of a day, whereby each frame represents 1 hour. And as you can see, there are a lot of activated pixels, which may or may not be lightning. On a more granular level, this is even more difficult. The graphic to the right shows us what we actually see under the hood without being grounded in the context of the Earth. As you can see, it's extremely difficult to tell which of these points in a 3D space correspond to lightning events. And at this point, even domain experts have difficulty distinguishing between activated pixels that are lightning and those that are noise. So this leads us to our scientific question. Can we use machine learning to find patterns in the data that help us identify lightning? And now my colleague Satyarth will walk us through some of the aspects of machine learning.
Thank you, Emmanuel. To answer that question, honestly, we don't know. But looking at the data, we think we can do something. And hopefully by the end of the presentation, we will have a better answer for you. So here's what we have. A really messy, noisy data on the left that doesn't seem to make any sense. And the output of the current filtering system on the right, which is majorly based on scientific thresholds. Although it seems to be less noisy, it still doesn't help us pinpoint what is lightning and what is not. What we aim to do is to leverage the benefits of machine learning to maybe find some hidden patterns that are not directly evident. So here's a pipeline that addresses this problem. Because our sparse dataset is so huge, we define a format to crunch all this information. This module in our pipeline is called the data processing module. Getting into a little more detail, we take our huge raw data, tile it up across space and time to create smaller patches, and compress each patch across time to reduce the size of the data. The diagram on the right shows the magnified version of a single patch with a spatial dimension of 32 pixels plus 32 pixels, which corresponds to an area almost as big as the size of the state of Colorado. Across time, we create each patch to contain information for half a second. The blob in the plot is a potential candidate for being a lightning event. This plot on the right shows the temporally compressed version of the patch. This helps the data become a little less sparse and a little easier to explore and interpret. Next, I'll ask Julia to explain the further modules.
Yep, thanks, Satyarth.
So after the data has been processed, we can proceed with the next step in the pipeline that consists of dimensionality reduction. This means that we want to reduce or compress the information which is encoded in our data. A standard technique for dimensionality reduction is to use an autoencoder. This means that we take a 2D image that we have created before from the raw data, we feed it into a neural network, and we obtain a representation of this image that lives in a smaller dimensional space. After applying this process to our whole dataset, we obtain an entire set of representations that capture the main features of the original images. And then we use these representations for the final part of the pipeline that performs clustering to discover groups of similar examples within our data. So we take the lower representations that we found before, we cluster them, and in our setting, ultimately the ideal goal is that images that contain lightning and images that contain noise will be assigned to separate clusters. So let's have a look to some images from the green cluster. So we notice that we are indeed capturing some similarity of the images here, but this similarity seems to be heavily influenced by the position of the signal in the images. For example, this cluster contains images where a signal is in the bottom right corner, and this other cluster images where a signal is in the bottom left. And this is an issue because the position is not really informative of whether the image contains lightning or not. What is more informative is actually the shape of the signal. And here I'll ask Emma to explain how we address this issue.
Thank you, Julia. One way to focus on the shape of the data instead of its position is to change the way it's represented to our algorithm. Specifically, we represented the data as a graph instead of as an image. This is a plot of 8,000 sample patches after they've been represented as graphs. You can see that the points form tighter groupings than we obtained previously with the image autoencoder. Looking at some example points from cluster 1, we can see that the patches contain small pairs of points that have a similar structure, but different locations in the image. This is good because it means that our model can now focus on the shape of the data and not its position. And if we look at points from cluster 2, they also have similar shapes but different positions, as desired. Given these results, we plan to continue to use this graph-based approach in our future work. In addition to testing the graph-based representation, we also experimented with a different metric, the Gromo-Vesserstein distance, which is blind with respect to position and focused on the shape of the signal. We found that when we used the Gromo-Vesserstein distance on raw data, we were able to successfully group together images that had very similar shapes. This is promising, and we propose that this is also a useful metric to use in our future work. In closing, our team has been asked if it's possible to use machine learning to find patterns in the data that can help to identify lightning. We have found that yes, there is structure that we can exploit. We discovered that standard methods are focused on the position of the data within an image, which is not desirable. But we found that graph-based representations and the Gromo-Vesserstein distance lead to better clustering results. Overall, we applied machine learning to identify lightning structures in datasets from satellites. This work will enable us to find crucial lightning events to assist in the timely detection of severe weather. These results will contribute to protecting people and property from tornadoes and wildfires throughout the Western Hemisphere. Before we leave, we'd like to say thank you to the entire Lightning team who made all of this possible. Thank you also to our sponsors for their support, especially Lockheed Martin, Microsoft, NASA, and FDL. And finally, many thanks to you, our electrifying audience, for listening.
Thank you so much, Team Lightning. That was really fantastic and really relevant as I live in a place that has many severe weather events. So I'm very excited about what you're doing. And I'll go ahead and bring up Bill and our awesome panel.
Wonderful. Thanks, Sarah. And I feel like a charged particle now. Great job. So I think it's clear that this team demonstrated their ability to more accurately characterize and identify lightning events and distinguish them from other phenomena, which can be an important contributor to improved severe weather events. So joining us for this panel, joining Scott and I for talking about this is Samantha Eddington, who's a systems architect at Lockheed Martin. So Samantha, what's your takeaway here on the science side in terms of, I think the team demonstrated an improved ability to characterize lightning. Can it help us really give better warning and better prediction to extreme events in weather?
Yes, so it's really exciting results because I mean the GLM instrument that they talk about has been on orbit gathering data for almost 5 years now, and still we are able to possibly upgrade its performance, even though we can't go up and change any of the hardware. So that's really exciting. And if we can do a better job creating the final lightning data product that is seen by the forecasters and atmospheric electricity researchers, then that can really improve their ability to predict as the severe weather that the team was talking about earlier, the tornadoes and predict the wildfires, which is very exciting for me in California, which is currently on fire. So I'm really excited about that. And you also got to see kind of the raw data, which most people don't see for instruments, like any instrument that you would go and look at data that you might see on the news or online. It's going to be processed, and there's a lot of processing that happens behind the scenes before you see these images or the data. And so you could see from this presentation just how much processing we have to do on the ground because we want to get all of the lightning data on the ground so that we can see as much of it as possible. So a lot of noise comes with that, and you have to filter it out on the ground. And seeing some of the machine learning techniques and how they might be able to help us do that is very exciting.
Well, it's amazing because you raise an absolutely important point here. This is not just about advanced or improved data and analytics. It really is about sort of synthesizing an actual upgrade to an instrument, to your point, without actually physically visiting the instrument. And I think the implications for that are profound. Scott, what's your takeaway in terms of methodology and approach on the machine learning work that was done here and its broader application?
Well, first, just holy cow. I mean, just if you look at I saw the raw data, Samantha. I don't know how in the world you find lightning from that. It just looks like a mess. That was amazing. That's incredible. So that's just the holy cow effect. But what's interesting, if you look at the team, is you looked at autoencoders and whatnot, and you look at things spatial, and you on your own said, we need a better representation. These image nets and CNNs aren't going to cut it. And you went for graph networks. I don't know if you read Jeff Hawkins' book yet on 1,000 Brains theory, but he has this conjecture that what we learn in the cortical columns in our brains and our neocortex is a reference frame. And we have some of the winners of the Turing Prize are now thinking about, capsule networks, where you actually try to learn the reference frame of what you're seeing, and that is much better than actually trying to just do it with a CNN. So I think you're onto something here, and I would really love, afterwards, connect me on LinkedIn. I'd love to know your thoughts about what Jeff's thinking, and how can you advance the field of AI? Because he's thinking that sort of is going to open up the whole new area, Bill, in artificial intelligence, to go after the holy cow effect of taking this jumble of data points and saying that's lightning. That's just incredible.
Yeah, fantastic. Well, that's awesome. Well, thank you very much to our panel for those comments, and thanks to the team and a wonderful job. And again, as the team already did acknowledge, I want to once again acknowledge our partners on that team, which were Lockheed Martin, of course, and NASA Earth Science within the Science Mission Directorate, and Microsoft, who helped support the compute for that incredible work.